Good morning. I am Emilia Cioroaica from Fraunhofer IESE, and I will present the results of a comparison study between safety and security analysis techniques. Growing adoption of new technological advancements within the automotive domain is highlighting multiple safety and security concerns. Aiming at reducing the errors humans make on the roads, deployment of novel and intelligent technological solutions are likely to introduce multiple vulnerabilities that can be exploited by attackers. In particular, because vehicles continue to transition into real cyber-physical systems, and as of today, we can already connect these vehicles to the internet and access their data with smartphones. We can foresee that in the future, vehicles will likely have even more options to connect to neighboring vehicles, roadside infrastructure, and even smart homes. In this way, automotive systems become part of a larger ecosystem, which aggregates not only other systems, but human actors and organizations as well. The flexibility of this emerging vehicle infrastructure supports the business growth within automotive smart ecosystems by enabling vehicles to communicate and collaborate dynamically during operation. At the same time, this evolution brings additional safety and security concerns due to the communication channels being introduced by an open environment. Looking to explore how current approaches can support the safety and security and co-analysis, in our paper we have summarized evaluation results of the state-of-the-art of methods applicable within automotive domain, focusing on collaborative vehicles by considering that modern vehicles are complex systems formed by a network of embedded control units interacting with each other and expected to accommodate runtime updates or adaptation of their functionality. Generally, embedded control units within a vehicle may be connected to multiple internal networks where they form different functions. For instance, some ECUs may serve as gateways that transform and share information between different types of networks. Architecture flows can expose intra-vehicle information to inter-vehicle communication without an information barrier, resulting in vulnerabilities that can be exploited. Therefore, from a security attack perspective, such embedded control units represent an effective target. Moreover, the safety-critical nature of vehicle enables us to reason of the safety implications of malicious attacks. Last but not least, even though addressing safety considerations in the automotive domain is a well-established practice, security considerations have only grown more prominent over the last decade. In our analysis, we have evaluated four most common methods. FMVA, which follows a bottom-up approach starting with systems design, and for performing FMVA, a system must be divided into components such as sensors for distance measurement, network devices, ECU controllers, and in general, this method maintains the focus on single components vulnerabilities while documenting their impact on the overall system. Then Sahara and chassis, even though they do not focus on single components, are also bottom-up approaches that base the safety and security co-analysis on functional decomposition of systems. Sahara performs a functional decomposition of systems, whereas chassis performs a behavioral decomposition. And then the STP ASEC, which on the contrary takes a bottom-down approach, starting by identifying accidents and system losses. And afterwards, the analysis is conducted with a focus on control loops between components in order to identify if an error of control at the higher levels can potentially result in a vulnerability that can cause an accident or a loss. For exemplifying these safety and security co-analysis methods, we have analyzed a use case from the automotive domain which is general enough to ease the mapping to similar domains such as robotics, while allowing us to be specific in the explanations. Through infrastructure-to-vehicle communication, a Platon leader receives information from a roadside unit about an imposed speed limit, and following a certain communication topology, the Platon leader further on sends the information to the Platon members via vehicle-to-vehicle communication. In a platoon, all vehicles apply the same speed and acceleration at the same time by maintaining the closest reasonable distance. And this maneuver reduces air friction and implicitly reduces the fuel consumption. By iterating over this use case, we have analyzed the stated security and safety methods, and we have groups defining according to multiple differentiating factors, such as the type of approach, the needed artifacts, creativity of analysis techniques, application phase, generated artifacts, risk evaluation, usability, and efforts. More details can be found in the paper, but in general, for the type of approach, as we said, FMVA is a bottom-up approach, then both Sahara and chassis, even though they do not focus on single components, are also bottom-up approaches that base the safety and security co-analysis on functional decomposition of systems. Sahara performs a functional decomposition of system itself, whereas chassis performs a behavioral decomposition. STPA-SEC, on the contrary, takes a top-down approach, starting by identifying accidents and system losses. And afterwards, the analysis is conducted with the focus on control loops between components in order to identify if an error of control at the higher levels can potentially result in a vulnerability that can be caused and can cause an accident or a loss. It maintains the focus of on single component vulnerability while documenting their impact on the overall system. Then both Saharas and chassis, even though they do not focus on single components, are also bottom-up approaches. With respect of needed artifacts, FMVA needs a physical decomposition diagram of a system. Chassis requires various forms of use cases and sequence diagrams at the start of the analysis. And Sahara requires functional decomposition diagrams of the system. STPA-SEC needs some non-standard artifacts, such as definition of accidents or losses for the system, and eventually hazard analysis. Some more details can be found in the paper. And if you have further questions and you would like to continue the discussions, you can also contact me. Thank you.